In this video, this is part 2 of chapter 4, where we're going to derive or understand why the equations for this kind of motion are the way they are. So in chapter 3, again, we're familiar with this situation. Notice that I now accounted for a more general situation in chapter 3 where I didn't start at 0. I still have a constant velocity. So all this green stuff, chapter 3. My velocity is constant, which means the slope of my xt graph is constant because I put x on the y-axis and t on the horizontal axis. And this definition of velocity, delta x over delta t, corresponds to the slope of this graph. We also know I could rewrite v. You practice this on the worksheets. I could expand the delta operation and clearly state that it's I'm doing a final minus initial, right? So if this was slope, this is how I could calculate my rise. This is how I could calculate my run, and I just realized I used x naught there. I'll call this my initial. So this is my initial position down there. My final position might be, over here. But really, I could that's v, that's true. But what if I want to find out any position, or I ask, is there an equation that tells me where I am anytime within this t? Where that ratio is constant for any point in there. Could I get an equation that could predict where I am? And the short answer is yes, because this is a line. So the form of this line, the mathematical form of that line, is y equals mx plus b. And if we look at that line, we can see that what's b? It's my y-intercept, so that's x sub I. So I'm going to take this from math world over here to physics world. Maybe I'll change the colors. So I'll go into physics world. So the y, my y-axis, is actually my position, right? So my position. And implicit in this, hopefully you're okay with y as a function of x. So this is really x as a function of time. What's that equal to? It's my slope. M is the slope of a line. Well, what's my slope here? It's my velocity. And what's my x value? In math world, this is the horizontal axis. In physics world, this is the time axis on this graph. And b is the y-intercept. So that's plus x sub I. So I can, it looks like a different equation, but it's really just this equation expanded out. What do I mean by that? Well, if I look at this equation, right, I've got xf minus xi, blah, 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 blah. Now there's a simplification here because I just have t in there. So I'm going to go, if t sub I is 0, then I could pick any arbitrary tf in here, right? Like in other words, I want to motivate or derive an equation for where I am at any point in time during which my velocity is constant. So if I apply those same conditions mathematically here to the equation, I want to replace ti is going to go to 0 because I'll just start at 0. And this tf, basically I'm going to say, you know what, I want to find out where I am at any time. So tf I could just represent as t. Well, if you do some algebra here, what ends up happening? If I get rid of my ti, because it's just 0 anyway, I get v equals xf minus xi over t. If you multiply both sides by t and then add xi to both sides, what do you get? I get v times t first, then I add x sub I to both sides, and I get that. Or, since I'm trying to find out at any time t, so this t has, whatever this t value is, that corresponds to this position, right? So that t final, if this is my tf, that corresponds to xf. So now you can get the same equation different ways, basically. Okay? So we have an equation for constant velocity. We want to ask, and we're going to park this question for a sec, we want to ask what in constant acceleration, so if you have acceleration now is equal to delta v over delta t, and it's not 0, so it's not trivial. Okay, so there's my velocity is actually changing. Question we're going to park right now is how can I figure out where I am? Okay, to do that, let's just borrow from chapter 3 again. So in chapter 3 we're going to use the same kind of analysis, but we're going to use our expanded motion, which is changing velocity. So not x anymore. I'm going to start with a changing velocity, which means I could have an initial velocity. And if I have constant acceleration, it means the slope of this graph is constant. So the shape must be a line. Again, it could be negative, but for now we'll just keep it positive. And that happens over some time frame. But we know that the slope of this is acceleration. All right, let's derive the equation there. Well, y equals mx plus b is the mathematical description of this line. We have a slightly different graph. Oh, this is still my time axis. So in math, my y-axis is the vertical axis. Well, here in physics, what's my vertical axis represent? It represents velocity. What's my slope? That's just my acceleration. What's x? It's my time axis. What's my y-intercept? Some initial velocity. Ta-da! I now have a new equation that incorporates the role of acceleration. So how fast I'm going at any time t. So you could really, I'm going to erase this, but you could think of a more formal definition would be v as a function of time, right, is equal to this. So you give me a time over which I'm accelerating by that amount, by this amount. You add on my initial velocity. There's my new velocity, v equals at, okay, plus vi. Acceleration is just the slope of this line, so we have an equation for that there. What about my position? How can I get my position? Well, to do that, I'm going to use something from chapter 3. And the thing I'm using from chapter 3 is this idea that if I have a velocity time graph, in chapter 3 they happen to be constant, right? The idea we're going to use is the following. The area under the VT graph, or area under, I'll spell it out this time, under VT corresponds to my change in position. Now, so we're getting close, right? So the question is, what about, do I have an equation for where I am? Because I have one here. For this simple motion, I've got a nice equation for my position. You give me all this info, I could tell you where I am. Now the motion got more complicated. Can we get an equation that still tells me where I am if my motion is now like this? Short answer is yes. We're going to do that by doing this. The area under a VT graph tells me my delta x. That's not quite the same thing, right? But delta x is equal to where I am minus my initial position. Aha. Right? And my initial position is just a constant. It's a number. It doesn't change. So you could see that if I can get info on my delta x, I've got my x in there. Why? Okay, just in case this helps. If it doesn't, throw it out. But I rearrange this. I go, x is just where I started plus my displacement. No duh. On a previous worksheet, that was the letter D. But there's x. So if I can get my delta x, I might be able to get that. Okay, so that's what we're going to do right now. The way we're going to do that is going to use this idea. Notice that when I said the area under my VT graph is delta x, it worked because the units work, right? So if I got meters per second times seconds, the seconds cancel and I get meters. That's true no matter what the shape is. What changes with the shape, the reason it's easy here is because I have a rectangle. So computing area actually corresponded to doing this kind of math. V times t gave me a delta x. But here something's different. My v isn't always the same. So we're going to do something kind of sneaky. What we're going to do is use a whole bunch of little rectangles. So the first question we're going to ask is when we say the area under the VT graph, does it still correspond to delta x? That's question number one. Does it depend, does this is this true only for this shape? Question number one. Second question is, okay, if it is true, how do we calculate that area? All right, so here we go. So the first question is it true? And it's going to require, yikes, whoa, there we go. It's going to require, it is true, if you use approximations. For those who took calculus, this is going to look very familiar. If you didn't take calculus, don't worry. Think of this as a little pre-calculus, right? But the idea still holds. So the first thing we got to answer is the area under a VT graph corresponds to displacement, but we only saw that when we had rectangles. So the first thing is I need to convince you that we have rectangles. What? Mr. Cachner, I see a slanted line. I don't see any rectangles. Well, yes and no. So I'm going to semi-zoom in on this. So if I have a line that looks like this, and I wanted to find the area under this graph, is it still displacement? This is qualitative. We won't end up with a complex math thing yet. I just want to convince you that the shape of the graph does not change the fact that it's a displacement. What I can do is I can approximate this line. How? Well, I could mark off, I'm going to mark off some increments here. I'm going to look at my motion during this time, they're even increments. You get the idea. Okay, so I'm putting even increments here. And if it's not exactly even, just pretend I drew evenly. Right? So let me do that. And we'll just go from there to there. So I have even increments. Well, what I could do is I could draw a rectangle that goes up to, so I have a time there, right? And if I wanted a rectangle, if I want to find the area, the easiest kind is base times height. Well, what height could I pick? I could pick a height where the line cuts through just the middle. Now, I know you might not be able to see that on the video, but I think you kind of get it. Watch what happens. I'm still a little bit off. I kind of want to go like straight across, like that. So basically at the top of the rectangle, you could see that I'm overshooting a little bit, but I'm undershooting a little bit as well. I'm going to keep drawing this and maybe it'll become clear. See how there's a little overshoot, but over on this end I'm undershooting? And if you just do it right there, it's a little clearer there. I've got a little undershoot over on this side, so I'm a little bit below, but over there I'm a little bit above, so they offset. So the area that I'm not capturing in this little gap, right here, so I'm going to block that shaded in area. Well, that area that I'm missing is actually the same as this area. Right, so I keep it symmetric. So if I just do this over and over again, I can actually, I really just have areas. So the idea is, since now I have a rectangle, and we're back to the old graph, right? I just have a rectangle. Since each bar is a rectangle, so this is not a mathematical proof by any means. It's a conceptual idea that will help your brain, in case your brain is stuck on the idea that the only areas I could talk about that show displacement are rectangles. I can basically say that since the area under the whole graph is actually equal to the sum of a whole bunch of rectangular areas, right? And each of these were little delta x's, a little delta x there of that much, that area, another one, then that's just going to be my entire delta x over or throughout t. So I can still talk about area under a graph meaning displacement if I just think of any area under the graph as a whole bunch of rectangles. That's how the logic works. Remember the if-then logic idea from chapter 1? If I believe that the rectangular area of a VT graph actually corresponds to delta x, then I can take any shape VT and represent it as a bunch of rectangular areas. So this whole area, even though it's a different shape, still has to be delta x. Okay, now that takes care of question number 1. The good news is that's great, right? There are no exceptions. The area under VT graph is still delta x, or displacement. Let's actually calculate it now. And to calculate it, we're going to need some equations, sort of. We're going to do the following. I'm going to redraw that, and then we'll find the area under that, and we're going to go for broke. In other words, we're not going to start at a velocity of 0. We're just going to say I'm at an initial velocity. Over some time, so maybe I'm starting initial velocity, and I'm going up this way for a certain amount of time. I'll just call it t. I guess to make it clear that I'm not talking about just that, I'll go tf. Okay. All right. So how do we figure out the area under this graph? Well, let's just talk area first. We know that if I do the following. The nice thing is there's a rectangle here. So there's a rectangle, but there is also a triangle. Okay. We also have an equation for this line, right? The equation for the line is my velocity is just equal to, remember this, there's a slope here, of a, at plus v sub I. Okay, so let's figure out this area. Let's do the easy one first. So our total area under this, I'll do it in green, so the big area is equal to the blue area plus, so there's a blue area plus a pink area. So we got to figure out both those areas. The blue one's easy. That area is just base times height since it's a rectangle. What's my base? My base is TF. Now, let's keep it more general. We know the range is, let's say that this equation holds only for whatever t, the range of t where that a is constant. But I'd like to generalize it. Remember how we said this is my velocity at any t? So just to keep that all the symbols the same with the meaning, let's just say this is till time t. And in fact, I could take this t and slide it anywhere along this, right? So if I took this dashed line and moved it in, what we're doing still makes sense. I'll just represent that as t. Okay, so if we're interested in the area under this part, I would just pick a t that's over here, but the equation stays general. Okay, so, or if I keep that t and not t sub f. This is true for, I can get my velocity at any time t. Okay, so base times height. What's my base? My base is t. What's my height? Vi. Well, that's easy. It's actually just vi times t, but I'll just keep that. This is, now let's do the pink area. I have a triangle, so it's going to be 1/2 base times height of the triangle, but we got to be really clear. What height are we talking about? Luckily, the base is still t, so I'm going to go 1/2 t. That's the base. What's the height? The height is actually this, right? That's the height of that triangle. So what is the height of that triangle? Well, the height of the triangle is this point minus this point. But the point, that's going to be, that's VI, right? And this, that's V at t. V at time t. Give me a t, I can use this equation. In this case, if my t was only over here, then my v at time t would be over here, right? But we'll use this one. That's v at time t. Okay, so there's my base, there's my height. My height is going to be what? It's going to be my v at time t minus vi. So if this was 20 and this was 5, what's my height? 20 minus 5. Okay, so now let's figure this out. Well, this is going to be 1/2 t. What's v at t? V at t is this, right? If I wanted to figure out what that value was, you tell me a t, I have my acceleration, I add vi, and that's my v. So it's 1/2 t times at plus vi, that's this, minus vi. Well, that's just 1/2 t times at, that's just 1/2 at squared. So what's my whole area? Oh, and then, sorry, I'm wearing a pale shirt. Okay, so there's, you could pause the video and just read it if you want. But I just plugged in the values for v at t using this equation, which is kind of legible on my shirt. And then I just substituted, right? Well, I didn't substitute numbers, I substituted equations, but it's simplified. The pink area is just 1/2 at squared. So what's the total area? The total area is going to be the blue area plus the pink area. So I'm just going to swap these so you could see the relationships, but I'm going to go VIT plus 1/2 at squared. But what's area represent again? That's delta x. We're almost there. We have an expression for delta x. But our question was, do we have an equation just for x? So I'm going to erase all this, and I'm going to reuse this. I'm just going to clean it up, okay, into its more traditional form. And this is what's essentially in chapter 4. So we got all that done. And we now have a delta x equation. So I'm going to repeat, or actually I'm just going to clean this up. Okay, I'm going to go from here up there. What's delta x? It's actually where I'm at minus my initial position, because that's what the delta is, or my x at time t minus my initial position. That's got to equal VIT plus 1/2 at squared. Now I can, if I isolate for x, I have a position, right? I can tell you where I am. Where I am at time t is just equal to, I'm going to add x sub I to both sides. X sub I plus VIT plus 1/2 at squared. What's this look like? Well, you can graph it yourself, take your favorite calculator, you can go into Desmos, but the main thing, hopefully you'll see, it's the t squared. So the general shape is a curve. So here's x sub I. You have something like that, okay? The VI will do what? All these things will change the curvature. It's still t squared, but it could make it a little steeper, okay? We'll stretch it out a little bit, but it's still t squared. All right, so this is the most, usually what students find is the most intimidating equation in chapter 4. But we now have an equation for position. We already have an equation for velocity, right? And acceleration is just that. So we're good to go. All right. We will see you in class.